Welcome back, everybody. So just a quick note, I did put some Chapter 7 and a couple Chapter 8 problems just to kick us off. On Friday, we'll be cutting into Chapter 8. Chapter 8 is all about this, hypothesis testing. So you probably know what this is. I'm not sure how that makes you feel when you hear that word hypothesis testing all together. It makes my skin crawl. I'll tell you about that for a minute on Friday, and then I'm going to tell you what the camps do. I will say this before I go into everybody does everything wrong. I would say that Fisher made a mistake. Naiman and Pearson tried to correct the mistake and tried to make it mathematically accurate, and that started a debate, a war. So I'll tell you about what everybody's fighting about, but it's basically their definitions of distances. Okay, let's just do some more estimation. This is where I decided the class should kind of fall. It's at least a place where there's differences that we can understand. Maybe we all converge into the same answers, so there's a lot of commonality and agreement. So we must be doing something right here. So this gross disagreements in hypothesis testing, we must be doing something wrong. So, okay, these are fun problems. So let's jump into this problem right here from the book. I'm going to bypass all those S-squared variant problems because all of those details are in the book. It's also a midterm problem. If you have any questions about that, we will do a review session on Wednesday. So we can go through your midterm if you want, bring questions. We can also go through the simulation study if you have any questions about that. Okay, this example is also in the book. I think it's pretty illuminating. Xi is coming from a Bernoulli distribution with parameter p. So a model we understand well. So the model itself is pretty basic. So we like all these sort of basic models because we can exemplify our points without doing a ton of calculus. But I can exemplify quite a few things in this example that you could carry over to much more complex examples. So just real quickly, for this example, what's the MLE? We know what the likelihood is. We've written it down a million times in this class. I'm a weird grammar again, but that's got to be pretty close. So what's the MLE? X bar. It's X bar. So X bar, sum of the Xi's over n, I goes from 1 to n. So we've got n data points in all of this. So we've derived that a bunch of times, write down the likelihood, take a derivative, set everything equal to 0, and you set everything equal to 0, put a hat on top of p's. Solve for the p hat. If you want to be really thorough, you can do your second derivative test and your first derivative test and make sure you've got a maximum, but we know this is the maximum. So, got to be a little bit careful that we have a couple data points in here. So again, the maximum likelihood estimator, we would have to be a little bit careful that if we only have one data point, the likelihood looks like a straight line like that, or like that, and so we do need to check the endpoints for things. But those are all the endpoints. So it so happens you get everything for free in that. Okay, we've got this. We've been studying that for a while. Here's a fact. This is not Minimax. We will kind of prove this in a second, but you could verify this if you found another estimator that had a risk curve that was lower, its maximum was lower than the maximum on that risk curve. So as soon as we do that, that would be approved for us. We find another estimator that has a lower maximum in the risk function. So we probably need to give us a loss function to proceed in all of this. So we're going to assume L2 loss. So this is just squared error loss. Then we can probably do some calculus. This is going to be true no matter what, though. It's not Minimax. So I don't care what the loss function is. It's still not Minimax. But at least we can do some calculus with the L2 norm. I'll warn us that this is probably the reason that the L2 norm appeals to most people is we don't need a computer, we can just do some calculus. Everything is smooth, and we can work out our answers. That doesn't necessarily mean it's a great answer, but it could be the basis for coming up with some good answers. So I'll just tell you that probably in real life, you should think about this more often than we're inclined to do naturally. So just moving on. So I picked something arbitrarily. So how much does it impact our analysis? A lot. So we'll think a little bit more about this. But this can be very subject to outliers or things like that. So if you don't actually know what the generating model is, this can be a very bad loss function to do. So there's a fiction in this class that I'm able to write down this stuff and I assume everything comes from that distribution. In reality, that's not exactly what happens. So it's something approximated by that. So be careful. Okay. Let's just work out the MSE. So the risk in our case, the risk for our estimator, that's this right here. Sometimes I call this EX. Sometimes I call this P hat. And sometimes we might even call it a different function, WX. I'll just pipe down when the book discusses the Cramer lower bound, they like to switch over to WX to talk about an arbitrary estimator. So no good reason for switching the notation there. So just be flexible to, a lot of times we call this a lot of different stuff. We want to be specific as to whether or not we plug the data in and it's an actual estimate versus it's an operator, it's a function, and it's an estimator. So just a few things to distinguish there. So the risk function for this, EX, and it's a function of P, the true parameter. Again, sometimes I call that P hat. I'll say for the MLE, this is just going to be the expected value under L2 loss of this thing. So I'll just write down a different way, P hat MLE minus P squared. You're taking that expectation. We've seen before, this can be decomposed into the bias squared of P hat plus the variance of P hat. The bias is just going to be the expected value of P hat minus P squared. Nice thing is, I don't have to think about positive or negative direction. You never will for any of the problems that we study. I don't even know what it is. If it's, I just tell people what do the residuals look like, if they're positive or negative. So it doesn't matter which direction this goes in, and everything always gets squared anyway. So an error to the left and an error to the right are the same things. So plus your variance for P hat MLE. And we probably know what these things are. So what's the expected value for the MLE? P. What's the variance for P hat, the MLE?
Sigma squared.
There's no sigma squared.
P times 1 minus P divided by M.
There you go. So this is P times 1 minus P divided by N. You can go back to the original definition and just look at the first moment and the second moment and work through them and come up with the variance. So standard Stat 101 sort of problem, this is the variance of everything. P times 1 minus P divided by N. Look at the first and second moments, work through the definition of everything. These are the easiest integrals that you could possibly take. So we could talk about these in review session if you're still struggling coming up with stuff like that. So this is P minus P squared, so this whole thing is 0. It's an unbiased estimator. And here is our variance. So the MSE, when the estimator is unbiased, is equal to the variance. So that's what this looks like. And we could even picture what this looks like. This is a parabola flipped upside down. So You could check that just by seeing the thing in front of the quadratic as a negative sign if I distribute that in. And so what does that look like? Looks like a parabola. It's going to live between 0 and 1, and it's going to peak in the middle of everything. So it's going to peak over at wherever x bar is and all of this, but this is going to look like this. So that's my risk function. So that's for p hat MLE. That close. We'll draw another one in a second. So the risk over here is 0 over 1. Over on the left end point, keep in mind if p was equal to 0, what would we see? We'd see zeros for our realizations. I average zeros, I get 0, so I nail everything. So over on the right hand side, exactly the same thing. If p was 1, so again, this is a function over p. So if p were 1, then I would see realizations that are all 1s. When I average them up, it's 1. So p hat is always 1, and I incur 0 loss. So this is 0 right here, just to be clear about that. We've said a lot of interesting things about this. We've always said over by the endpoints, everything is really difficult to work with. These are bad estimators. They actually nail the truth, right at 0 and 1. But things might be problematic right over there when things are really tiny. And understanding your uncertainty. So these variances, if p hat were 1 or 0, that thing is 0. So that's a little bit clumsy to say I've got no uncertainty about that. If true p were 0 or 1, that's a good thing. But you just got lucky because you can't distinguish yet 0 and 1 from 0 plus epsilon and 1 minus epsilon. There's a lot of variability in here. So lots of variability when p is in the middle, 0.5. This actually peaks at 0.5 right here, this thing. We're just looking at this function, so this doesn't have the estimator in it. So this thing peaks at 0.5. There's a lot of variability, lots of 1s and 0s. And so where does our risk come from? It comes from all that variability. Variability is an interesting thing. You might think it's bad. I tend to think it's good. So it just depends on how much there is. So variability gives us the ability to distinguish things. So it's all of your unique differences that I'm able to talk about. So I don't sit there and go, oh, the class is great, they're all the same. So I talk about your unique differences, your strengths, and where improvement can be. And that's different for everybody. I tend to think that's a good thing. So just in general. So the variability gives us the ability to distinguish things. And if we're building intervals, we do well right here, but there's a lot of variability in our estimators. So you might look at this and say, oh, I hate estimating things in the middle. I like estimating things on the end, but I tend to think differently, but I'm thinking about other criterions, like when I quantify my uncertainty. Stuff like that, and I come up with intervals. So I'm thinking about something a little bit more than just the risk analysis tells us about. But this is what that looks like. Let's consider another analysis. Let's do a Bayesian analysis. We've done this before for this example. So p hat Bayes. Again, we're going to look at the L2 loss function. So to do an apples-to-apples comparison, I can't change the criterion I'm using to evaluate the estimator. That'd be like changing my grading criterion for each one of you because of whatever reason. So you need to be at least semi-uniform in all of this. And if you're doing math, you better be precisely uniform in this. I try to do as good as I can. So, p hat Bayes, we've worked through this before under an L2 loss function, and I have to end up coming up with a prior. So I'm going to need a prior, and our Bayes estimators are defined within prior classes. So the way we average over parameters might change depending on things. So we probably need lots of reasons before we felt good about certain priors. So I haven't told you all the reasons why the beta prior is good, but I have at least demonstrated, or you've demonstrated to yourself it can work very well. So it can also work very poorly depending on how you hyperparameterize it. So I probably need to tell you a little bit more about hyperparameters, but we kind of see them as knobs, and things have gone right so far. So using these regularizers. So I'll just say this thing is going to be a beta with two parameters, alpha and beta, in there. Same thing that we did before. Very typically, I pick those to be a half and a half, but there can be reasons to pick other hyperparameters. And you can let this sort of risk analysis guide your choices. So the book goes through this a little bit. They don't fill in all the details. I'll ask you to fill in the one detail that they're missing. But our Bayes estimator looks like this. Sum of the xi's plus alpha over n plus alpha plus beta. This is the posterior mean. We've worked through that before. So this is conditional on all the x's. And very typically, I'll write down my hyperparameters in there. I think this is beyond the norm. Most people won't write those in, but we're in the classroom. I often do like to write them in, and if I'm going to adjust them or think about them, I like to write them down in my notation. So that's this. Any questions about this? Is this just obvious that that's our Bayes estimator? Done, right? I'm going to pause for 20 seconds and see if a question comes to mind. I said it so confidently that you're, of course there's no questions. That's the main thing. Why is that the Bayes estimator again? Isn't there a definition for Bayes estimator?
It's a likelihood function times your prior.
That's a posterior. So that is certainly related.
It's a linear combination of information. It's, I don't know the exact wording of it. It's like a linear combination of your prior information and your the distribution you're working from.
I think what I said was it's a superposition between those two things. It may be a linear combination, and certainly in the normal case, in the Gaussian case, it's a weighted average and it's a linear combination. And that seems to be a linear combination between the data, but it's not necessarily a linear combination. That can happen. Superposition. So again, multiplication of prior times likelihood, that defines Bayesian. So you do that and you start thinking about that random variable, that parameter that you don't know, and you think about it as a random variable, you just did something Bayesian. Now, if you want to come up with a different name for it and say I belong to the Hubula camp, and that's what Hubulas do, I just made that word up. I hope I didn't say anything offensive. I worry these days. It's not meant to mean anything, but you can call it whatever you want if you don't want to be affiliated with the Bayesians. So I know that we're pretty rivalrous these days. So you can call it whatever you want. I'm still going to think you're Bayesian. So what's the definition of a Bayes estimator? So I said this is our Bayes estimator. But I just kind of wrote it down, and the book did the same exact thing. They're like, your Bayes estimator is main, boom, and they haven't even told you what a Bayes estimator formally is. They're kind of saying, well, it's an estimator out of the posterior. That's true. Posteriors might have means. They certainly have some characteristics, not necessarily means, and a lot of us jump at means instantly. And no matter how hard I try to break you of that habit, you're going to do it anyway. There'll be a day that you'll go, yeah, I should listen. But that's okay, I'm like that too. Just remember. So what's the definition of a Bayes estimator? Somebody tell me as concisely as possible. I agree it has something to do with likelihood times prior. That's what makes you a Bayesian. What's the Bayes estimator?
It's an estimator that's integrated with principal Bayes.
What's the Bayes estimator? I hear some word salad, use the principle of Bayes. Bayesian principles. How do you do it? What is it? There's some calculation I do. Yeah, you keep invoking the word expectation, maybe. It may be. So, not saying no. Some function. More word salad. Functions, spaces, principles. These are all good things.
And then minimizing the Bayes risk.
Minimizes the Bayes risk. So what is, it's the argument that minimizes the Bayes risk. What's the Bayes risk?
It's the integral over the risk times the prior.
Very good. So we'll take that argument that minimizes theta. So we'll let theta be our parameter, just so that we can define this more generally. Integral of the risk function. I've got my estimator in here. I'll write down as EX. That's theta hat with everything plugged in, but I'll just be real specific about where the data is, times our prior. So it's a weighted averaging. It's the argument that minimizes the weighted average of the risk curve. So if I were thinking about risk functions, the integral is the area under that risk function. Of course, I'm superimposing or I'm weighting with the prior, and I can kind of budge around this shape. So I might not just be thinking about what this looks like precisely, but I might want to weight over it. If I didn't feel like changing the shape of the thing that I'm building the area under, this is an interval between 0 and 1, I can come up with proper weights, i.e. things that add up to 1, which is perfectly fine, and just uniformly average over that interval. So I could use a uniform distribution between 0 and 1. Again, this is going to happen between 0 in omega theta, or let me just rewrite it like this. All over your entire range of theta. For p, that's between 0 and 1. So I could use a uniform prior and try to come up with analyses that minimize your average risk. I incur risk differently at different parts of the space, and maybe I think about those different parts differently, so I weight them and then I want to average. What does that mean? I'm probably going to repeat the process over and over again. So if I want to be good on average, I'm kind of thinking about something frequentist. In my mind, I'm going to repeat this process. Some of the times I'm going to win, and some of the times I'm going to lose, but on average, I don't want my losses to be too big. So I want an estimator that kind of fits in the middle somehow in some sense. So I think that kind of makes sense. So this is theta hat Bayes. That's your Bayes estimator right there. So let's just rewrite this thing down. So it might not be perfectly obvious that this right here is that, but it does seem intuitive. L2, I've said that has something to do with means. What other mean would it be? It would be the posterior mean, right? Let's just work through that. So let me rewrite this just a little bit differently. So I'm going to arc minimize theta, integral risk function, I should be a little bit more careful right here. This actually does not have x built into it. X is gone in the risk function. So this is just the estimator itself. So I might get rid of that and just put a dot, that it's just the function itself. X has been integrated out. So it's no longer part of this. So this is what we might call theta hat. So I'm going to get rid of that X right here and just remind us, we've already gotten rid of all of that. That's just the estimator right here. So weight everything over theta. You can put your bounds down here. These are definite intervals. Okay. The risk function is an integral itself. This is what I was alluding to. So this is actually double integral. The risk function itself is the loss function. It has the data plugged into it, at least as an argument. And I'm going to average with respect to the sampling distribution. So So I'm seeing what happens on average in terms of the data space. And I'm weighting that right here. So this right here is risk. And then I multiply that by pi theta, d theta. And I'm going to arc minimize over that. Same thing, I'm just writing down explicitly what that risk function is. Let's just come down here. Rewrite this again. So I'm going to drag this inside right here. So I have sampling distribution times prior. It's starting to look familiar to us. So if I take the functional form of the sampling distribution, I multiply it by a prior, it's starting to look like a Bayesian's posterior distribution. So it's got all the pieces in here. Let me actually write it up tall. We can regurgitate that picture in a second. So this thing is just going to be the arc minimizer over theta, integral. I'm just going to tuck my prior into everything. If you don't like saying that, you could say your weighting function. So, doesn't need to be prior beliefs on what you actually believed about anything. It could just be how much you value certain parts of the theta space. So this is going to be loss function EX f of x given theta times pi theta, and I'm going to dx d theta this thing. So I just tucked everything in there. I'm going to just divide by mx and multiply by mx. So where mx is the margin of the data. So this is f of x given theta times pi theta d theta. Again, this is over all of the parameter space. So all of my integrals are definite integrals. So this is over the entire x space, that's the entire theta space. So that's just the margin of the data. So this thing, I can re-nickname. This is our posterior distribution. So that's the posterior. I.e., if you do analysis off of this and start integrating under this and thinking about it as a probability function, or you could give that another name, I'm going to think you're Bayesian and that's posterior. But you might have a different name for it. So like reliability function or something like that. So again, people like to change the names periodically. So be used to that, it will not go away. So I can also do a little bit of rearrangement on these bounds. So I probably need to say a little bit more about this, but this is the positive function right here. This is all positive stuff in here. Sampling distribution is positive, that's positive. If the integrand is positive, you can apply Fubini's to everything. It's not an additive integrand. You can always do this. I'll let you attend your measure theory class to go through those details, but I'll put this in the category of grad school Fubini's. When is it true? Almost never. Almost always. There are cases when it's not. So sometimes you might need to check, and we'll look at one of those as we get into Cramer round. We'll discuss that. But these are interchangeable. If you're looking for the permission slip, it's this thing. Fubini's theorem. And so I'm just going to rewrite this. And this is going to look like integral. This is going to be my loss function, theta ex, times my posterior distribution, d theta. I've got an mx right here that I'm going to pull outside of that term, d theta. So this is just that mx. I'm interchanging everything and I'm pulling that outside. Just like I tucked the theta, pi theta in, now I'm reversing that step after I apply Fubini's theorem. So again, this is arc minimizing over theta. So this is a function of theta. And I can look at where all the thetas are involved in all of this. It's just there. So the outer integral is just constant stuff that I'm integrating. But in terms of a function over theta, I'm just multiplying something in. I'm not changing anything. So only the inner integral does anything for us. And the other thing is just multiplying by some positive values. So if I want to optimize this whole function as a function of theta and relate it back to x, all I need is that, because there's no thetas over here. I missed one of these, right? This is a dx. So sorry about that. That's dx, d theta is there. So we just need to look at this integral. And so I can get rid of all this stuff. That integral sign and that stuff. And so our Bayes estimator is just going to be the arc minimizer of this loss function times that posterior. What would you call this integral? What would you name that? You don't even have to be clever. It's an expected value for sure. So you just call it the expected value.
Expected loss.
It's expected loss. But you might want to be specific. Not all averages are the same. So if I walked into a room and I say, oh, I break up space and I average, done. That is my entire career. That is the whole thing. But it's the way in which we do it, and average with respect to what and why. It's the posterior expected loss. So that's what I would call it. So this is the posterior expected loss. I love this thing because it's a conditional statement. It's conditional on X too. So it's got X built in, and I automatically adhere to the conditionality principle because I'm conditioning on X. So if I add actual X's and I plug it in, I can figure out my conditional answer by doing this. I also adhere to the likelihood principle in some sense. At least I'm conditioning on the sufficient statistic. So I've got that here. Where did it come in? It came through the likelihood function. Because that's the way I'm thinking about it because I'm operating over theta. So I shouldn't say that I haven't violated the likelihood principle, but I at least am adhering to the sufficiency principle and the conditionality principle. So likelihood principle light. I'd have to talk about what I was thinking about when I derived my prior. So it's kind of a funny game. I tend to like things when they're funny, so it's not a big deal. So posterior expected loss. We'll come back to those in a minute, the Poisson and the Cramer thing if we can get there. So our Bayes estimator, theta hat Bayes, is just equal to the posterior expected losses, and I'll just write it down one more time for your notes. Again, I get rid of the outer integral just because it doesn't have anything to do with theta. So whatever I'm doing there isn't changing any answers. I'll let you think about that. So you can try this for any example, any posterior, any loss function you like, and if you want to optimize the inner integral, you can go back to this double integral and think about it that way and optimize it, and you'll get the same optima. Okay, so different way to think about things. Again, I like it because it gives me, I think about it inferentially when I'm doing this. When I'm thinking about all of this, I might be thinking about a simulation study. So how would I approximate this integral? I'm sampling from my posterior, I'm plugging it in here, and then I'm simulating that, and I'm seeing how close I am on average, and I repeat this process over and over and over again. So for me, all of this risk stuff, I just see for loops and simulation studies. Because I get to pretend I know theta and generate everything. When generating the data, theta generated the data, along with F, the model. Okay, now we're back here. So I just said our posterior expected loss is our whole thing, but for our problem for L2, we have this. We need to optimize EX right here. That's going to be our optimal estimator, whatever this thing is. If you don't mind, I might just call it E for a second and just say this is E, it's my operator that I'm going to use to estimate everything. I just don't want to take my derivative and make it seem like I have to employ a chain rule, because you don't. So the notation is just a little bit easier. Maybe I think about this way. So squared times my posterior distribution. So I want to optimize this thing. How do I do this and find the arg minimizer of this? I take a derivative. What am I wiggling around? I'm wiggling around E. So I'm going to take a derivative over E. I just didn't want to say I'm taking a derivative over E of X and you think of it as a compound function. I'm not thinking about it like that. So if I want to optimize this, I can do it directly. So dE integral E minus theta squared pi theta given X d theta. I can slide that right inside, right there, just because there's no E's on the boundary of the space. There's nothing that I have to worry about. This doesn't have anything to do with E. The only E in here is there. It's in the loss function. So I can slide that derivative right through the integral. Again, this is Fubini's theorem, but it's because the parameter, the boundary of my space doesn't have anything to do with my estimator per se. So this is just going to look like this. Integral, I'll take the derivative right here. This is 2E minus theta. Derivative of E with respect to E is 1, so that's my chain rule. Pi theta given X, d theta is equal to 0. As soon as I do that, I should probably put like a hat on there just to show that I'm doing something optimal. So maybe I should have started with a theta and I turned it into a theta hat, but I already had a theta in the problem. So I didn't want to mince those two things. So this is pretty easy to work with. The 2 disappears. And factorize that whole thing out, get rid of it, and this is just going to imply integral E hat pi theta given X d theta is equal to integral theta pi theta given X d theta. This is the posterior expectation. That doesn't have a theta in there. That's coming outside, and then I'm integrating over the posterior distribution. It's normalized. It is the posterior. That integrates to 1. And so I'll just pop that outside. E hat, and remind us this thing is 1. So E hat is equal to that posterior expectation. If I change the loss function to the absolute value, it turns into the posterior median is the optimizer. 713 in your book is a really good problem to look at to try to explain that to yourself. They don't do it with respect to the posterior, they just show residuals in the absolute norm. And they have you work through that and show that the median is the optimizer. Same exact thing happens here, but it's going to be the median with respect to the posterior distribution. I would say the math is equivalent to that problem. So you might want to look at that. So for 0-1 loss, the Bayesian optimator is the mode, the maximum mean posterior estimator, so the posterior mode. I'll let you think through that as well. All of these are 1 or 2 line proofs, if you can set it up right. So stuff to think about. Here's fact. I'm going to give you 3 facts. all of these proofs are about 1 or 2 lines. Again, think about the definitions and what would happen if these things weren't true. So you might be able to come up with real quick contradictory proofs for this. Bayes Estimator. Oh, I'll say a few things right here. Bayes Estimators, and this is if the prior pi theta, your prior distribution, is proper, i.e. integral pi theta d theta is equal to 1 when I integrate over the whole space. So I can normalize it. The converse to this is not necessarily true, that if this condition isn't true, it doesn't necessarily mean something's not true. This is just a guarantee. So if our prior is proper, I didn't do anything super weird with my weights. They all add up to 1. So I can normalize everything. I don't have weird things going on with infinity, essentially. Then the Bayes Estimator is admissible. I'll let you think about that. Maybe think about what would happen if it weren't admissible. Bring in the definition, that means there's another estimator out there that dominates this estimator's risk function. It means that the risk function is always lower for some other estimator. This is not possible, and you can prove that just by the definition of what a Bayes estimator is. So that's cool. So Bayes estimators are admissible. It means something. So great. So something somewhere. Guaranteed. I'll say if Bayes estimators, if a Bayes estimator has constant risk, it's Minimax. I'll tell you what the proof is real quick in 1 sentence. Say it's not. So then I have another estimator that has a lower maximal risk, and then I think about what would happen to the area under that curve. It would be lower than the Bayes estimator, so that's a contradiction. So you can't lower that maximum and have it always lower than all of that, and it's lower than the risk function for the Bayes estimator, because the Bayes estimator assures that the area under that curve is minimal. So what would happen if I bring something uniformly lower than that curve and I look at its area, it has to be lower also, so the Bayes estimator is Minimax. See if you can reconstruct that argument in your mind. So this is cool. So this is fact. Here's another one. And I'll say this, unique Minimax estimators are also admissible. It's probably not that surprising. You're beating something somewhere. It may not be at that maximum, at that minimizing point though. I'll let you think about that. So there's a transitivity argument that you can use to show it. Again, 1-line proofs. If you type any of these questions into Google, you will get the proof. So it's not ChatGPT, people just written it up for you. So it's on somebody's PowerPoint. So I'll write that down too. Minimax estimators are admissible. I should probably say something about the uniqueness condition. I'm not going to write it down, but it just basically means that I could have some other estimator out there that's tying me all the time, and it's always on that, and I'm never lower than it. It doesn't mean that I'm not admissible. So it means that I've been tied by something else that's really good. We can write it unique. But Minimax estimators are admissible. It's just that you might have something that obtains that same maximum that's also lower in other places, and it can beat you. So that's cool. So what I like about this is there's something good about Bayes estimators. estimators. They can beat something somewhere, they can beat Minimax if I wanted to, if I ended up taking the risk function and making it constant, and making it flat. And one possibility for doing that is I need some toggles to be able to play around with the risk function. It turns out these are those toggles right there. So I can change this alpha and beta and change what the risk function looks like a little bit. And it turns out that the risk function has so much flexibility and the prior has so much control that I can flatten out that whole curve. So let's just look at the basic steps. You'll have to do one more step to complete this argument. But we can look at the MSE for this thing right here. So the MSE for P hat Bayes, again, it's just going to be the bias of P hat Bayes squared plus the variance of P hat Bayes. These would be some pretty nasty integrals to work through if you needed to. I would remind you, try to do everything the step 101 way if it presents itself to you. So you might know what the expectation and the variance of things are off the top of your head. You could probably derive those off the top of your head. So this is just going to look like this. I'm going to rewrite this. This I'm just going to call y plus alpha over n plus alpha plus beta, where my y is just the sum of the xi's. So we know how that thing is distributed. It's going to be binomially distributed with parameters n and p. So this is just going to be expected value of y plus alpha over n plus alpha plus beta minus p squared plus the variance of y plus alpha over n plus alpha plus beta. This is just going to be this. Expected value of y is np. It's a binomial. This is np when I take the expected value there. This is a constant, so it just shifts everything. And I still have my scaling factors minus p squared. No calculus required. This expectation that I took was an integral, or it was a sum. We didn't have to think too heavily about that. Same thing happens here, the variance. If I shift everything, it doesn't do anything. I've got this scaling factor, it comes out, and it gets squared. So this is going to look like this. 1 over n plus alpha plus beta squared. Variance of y is the same thing as variance of y plus alpha. If I shift everything, I don't change its variability. And the variance of y is n times p times 1 minus p. So the variance for a binomial. So this is going to be n times p times 1 minus p. So that's our risk function. And it can look a lot of different ways. Obviously, if I pick alpha and beta equal to 0, I'll get back the MLE. So this analysis corresponds to an MLE's analysis, but I might be able to think about things as a posterior distribution and integrate under curves and do things like that and explain that pretty easily. But I don't have to pick the MLE's analysis and do that. I could also try to adjust these. The book ends up showing that if alpha and beta are picked a particular way, our risk function will become constant. So this is going to be our risk, 0, 1, this is p. Here's what we drew last time. It's this parabola that's inverted. So that's our risk function for the MLE. P hat MLE, risk. And now I've got this other thing right here. It turns out I can pick values for alpha and beta and get a flat risk function. This is P hat Bayes. And all you have to do to figure out the values of alpha and beta are going to be to take derivatives partial derivatives with respect to alpha and beta, set them equal to 0 and do a solve. So there's a bit of algebra there. One shortcut you might be able to figure out real quickly is alpha and beta probably should be the same values. There's nothing special about alpha or beta. And in terms of symmetry, you should treat them about the same if you want to treat everything in some sort of objective fashion. I shouldn't bias one side or the other. So if I ended up letting beta be alpha in all of this, I just have one derivative to solve for. Take the derivative with respect to alpha and then solve for it. You'll get the same answer either way. So it turns out this is going to have alpha is equal to beta. Does anybody know what the value is? They write it down in the book, but they don't derive it for you. Does anybody know? Cool. Good candidate choice for a future exam. N over 4. Square root of n all over 2, or n over 4 square root of all of that. So it turns out that creates this flat risk function, and you might think about this, that there's a trade-off between these two estimators, the MLE and everything, that this one is constant. You might want constant risk all the way through the whole space, meaning no matter what P is, your analysis is going to treat everything about the same. It's kind of weird, because if n is big, I'm biasing the heck out of the answer to do that. So would I like to do that? Probably not. So I wouldn't advocate doing this necessarily, but if I were just a mathematician and I didn't care about anything else, I lived in abstract land and I would say, well, I picked it, it's Minimax, it's a Bayes Estimator, it's admissible, I have all of these mathematical properties. That's sweet. But I might also think, I'm biasing the problem so badly that I'm worried that I'm not even learning the truth very well. So you can play around with that and think about what all the trade-offs are and all these different criteria. But right now it sounds pretty good. So that this flat risk function maybe is okay. Maybe I'm willing to deal with the inherency of the problem, that I would have more risk over here. The risk over here is higher than it is over here, so there's a trade-off there, but I get things back over here as well. So I can't tell if both of these are admissible, but through the theory, that I can tell that both of them are admissible. So the theory without the 1 or 2 line proofs that you could conjure up will say that both of these are admissible estimators, meaning that there's no estimator out there that just beats it everywhere. And if you think about the MLE, it'd be pretty hard to beat it right here. I could certainly come up with estimators that beat it right here, that I say, oh, my estimator is always 0. So p hat's always 0. But then the risk function would do something like this. Or p hat was always 1. I just said, p hat's 1. I do really well at 1, and I can beat that, but I can't beat that. So it's still an admissible estimator. So it's good to use admissible estimators. It's not absolutely compulsory, but if you're not using them, you have to ask yourself why and whether or not it really matters. If you're using a flat risk function, just keep in mind, you're incurring that same maximal risk everywhere. So in some sense, people will call that the least desirable Minimax estimator, because you incur that maximal risk everywhere in the space and you never come down from it. Saying that, it does minimize with respect to that prior weighting that I'm using, a beta prior with parameters square root of n over 4, square root of n over 4. I'm averaging over in that particular way, and in that particular average, I'm saying nothing can beat me on average, in that type of average. So again, there's lots of trade-offs. So we get a lot of things for free, but we do trade for it. So maybe there's nothing that's actually free. Let's come back next time. Look at the Poisson example and try to motivate whether or not we can know we have like a minimal variance estimator. And that's the Cramer lower bound. So we'll pick up with that. We'll do an example, and then we'll cut into the proof. So if you want to save yourself a headache, glance at that proof beforehand. So I'll give you just something you can pick up on in the proof. How do you use Cauchy-Schwarz? So if you can answer that question in the proof, you must know the proof. That's it for now, you guys. Thanks so much.